everyone. Welcome to the first lecture on writing and understanding proofs. There's a bit of a different kind of lecture than I'm used to giving because it's not about the maths itself, but it's more about kind of a meta thing, which is how to do the maths. And anyway, I hope you find this useful. And as requested, we changed some of the exercises in here, or the demonstrations. They've been changed for ones that are relevant to what you've been doing in class. So I hope you find that useful as well. And let me just turn my camera off and we'll get started. Okay, so we'll just start with talking about what we're going to do. So I've said there's going to be at least 2 lectures. There's definitely going to be this one and the next one, but then I just put that in brackets in case we think of something else that we want to tell you. And over the course of the next 2 lectures, we're going to understand some of the main types of proof. That's the main goal of today's session. We're going to learn about mathematically formal writing. We're going to know how to verify proofs and check for common mistakes. So this kind of learning about the writing and verifying is for next time, but the common mistakes I'm going to address as and when we talk about the types of proof. We're going to examine some good proofs. And in the next session, we're going to examine some not so good ones, because it will help to compare them and to highlight the difference and hopefully the importance of mathematically formal writing. So yeah, today the main types of proof that we're going to discuss are direct proof, proof by contradiction, proof by induction, proof by contrapositive, and counterexamples. So for all of the proof types, we're going to explain the logic behind them. We're going to work through an example. And at the end of the session, we'll have some exercises for you so you can print screen and do them later. And as usual, we start with just definitions. So a proposition is a statement which can be said to be either true or false. For example, 2 is even, that's a proposition and it's true. 3 times 5 is 10. Okay, it's a proposition, but it's not true. And the sky is blue. And whether that's true or not depends on the weather, I suppose. Now, in this statement, I've used the word said here rather than proved to be either true or false, or something to that kind of language. And this is kind of a subtle point that goes into axiomatic set theory and logic. There's certain propositions where they are axioms, and there are certain propositions where there's no proof for them being true or false. And the classic example is the continuum hypothesis. Anyway, all this goes well above and beyond what we're going to discuss today. So sorry if that's a bit disappointing for you if you wanted to go into some axiomatic set theory. That's something we could cover later down the line if people were interested in hearing about that. But in any sense, a proposition, it's not, a question, it's a statement. So letting A and B be propositions, we're going to use this notation here to denote the logical negation of A. And that's just saying the opposite of A. So the opposite, the negation of all multiples of 4 are even, is a statement there exists an odd multiple of 4. That's obvious. This little angled thing here denotes and. So this is saying, this proposition A and B means either both A and B. And this one here with the upside down version of that says A or B. So the next one, this arrow here denotes that A implies B. So if A is true, then B must also be true. And a little example, if we take the conjunction here, the and here, so we have X is even and X is a multiple of 3, this forms one big proposition on the left-hand side, and that implies the proposition X is a multiple of 6. So A always implies A or B, and A and B always implies A. So if I have something, it always implies that thing or something else is true. And if I know that A and B is true, then it implies that A is true. So this is kind of strictly stronger information than this. And if I write these arrows with two heads on either side. A if and only if B, this is what we say. And it literally just means that A implies B and B implies A. So A is true if and only B is true. And in this case, A and B are logically equivalent. So the information contained in the proposition B is exactly the same information as what is contained in A. So for a quick example, x squared is equal to 4 if and only if x is equal to plus or minus 2. Both of these sides tell you the same thing. Now, if you get asked to prove something holds if and only if something else holds, then you need to prove that one side implies the other and vice versa. And it's a very common mistake that people make is where we miss one of them off by accident and we just prove that one implies the other. So I've just seen there's a message in the chat. Is it important to have two horizontal lines for these arrows? Not really, no. As long as it's clear what you're doing. I mean, a lot of this notation is, there's different styles that you can use. If you used a single arrow, then I think everyone would know what you mean given the context. But I think I like to use the single arrow one to denote functions and mappings, you know, the domain and the codomain with an arrow in between. So I like to use this one for logical implications. Okay, so if we have two sets and we're trying to prove that they're equal, so the proposition A equal to B, where A and B are sets, is logically equivalent to x belongs to A if and only if x belongs to B. So when you're trying to prove something, two sets are equal, what you have to do is prove this claim. So you have to prove that x is in A implies that x is in B, and also the reverse implication, x is in B implies that x is in A. And what this looks like here is actually called the axiom of extensionality. So this is one of the ZFC axioms, and you have to take this as a given. It is true in most people's mathematical universes, but if you're interested in axiomatic set theory, then kind of exploring what happens when you include or disclude these axioms is very interesting. But what this kind of says is, very simply put, sets are equal if they contain exactly the same elements, which seems intuitive. So yeah, this is what this means. If two sets are equal, then they are subsets of each other. And that's kind of how you prove equality of sets. Okay, so on now to the first type of proof we're going to discuss, and it's the easiest one, and it's direct proof. And as it sounds, you're just going to directly prove something based on the information that you have. So it's going to be the first thing you attempt in most situations. All you have to do, use the information you're given, straightforward implications, and you derive the desired conclusion. So the first example we have today is this one. So this is related to the topology work that you've been doing. So if we're going to let A1 up to AK, so we've got finitely many closed sets, and they're on it for some topology on a set X. Prove that the union of all these sets is a closed set. Okay, so by the definition of closed sets, we know that their complements are open. This is how you define closed sets in a topology, right? They're the complements of the sets which belong to the topology. I guess going back to what we were discussing earlier, there's a little C here which denotes the complement. Some people use a little line over the top to denote the complement. And yeah, there's just different ways you might want to write it. But that's why I sometimes, when I'm writing proofs and the notation has a choice to be made, I'll just write something like this, which makes it abundantly clear to the reader what I mean when I write this, this C here. So the complements of these sets AI are open for every I. In a topology, intersections of finitely many open sets are open. That's one of the key aspects of a topology. So we know that the intersection of all these complemented sets is open. Now, whenever you have any kind of statement which involves intersections of open sets, of complements of open sets, or complements of intersections, complements of unions. The first name that should pop into your head is De Morgan. And this is something which you saw in one of the earlier lectures, I think a few months ago, but it comes up time and time again. And so we're going to apply one of De Morgan's laws, and we see that the intersection of all the complemented sets is the complement of the union of all of those sets. So we get this nice little equation here by applying De Morgan's laws quite simply. The intersection of the complements is equal to the complement of the unions. And that's an open set because of the work we did earlier. In a topology, complements of open sets are closed. And this kind of completes the proof, right? Because you've got this open set here, you take the complement of it, you get the complement of the complement, which is just the set itself. So the union here is closed as required. That's the thing we're trying to prove. Now, I want you to pay close attention to the kind of language we use here. So we've got thus. We're specifically defining for every I in 1 going up to k. So, you know, I is specifically defined in the question. We're not leaving anything out. And we're kind of laying it out neatly step by step. Okay, the next type of proof we're talking about today is the proof by contradiction. So if we're asked to prove a proposition P, the law of the excluded middle tells us that P or not P must be true, right? This is very easy to see, right? If it's intuitive, it's one of the laws of reasoning. So if P was the proposition, there is a blue car parked outside. We don't know whether P is true or not for me, but we know that either there is a blue car parked outside or there is not a blue car parked outside. And that's what the law of excluded middle tells us. There's not some weird third possibility, sorry. So if we can prove that the negation of P is not true, it must follow that P is true, right? Because if I can show that there isn't not a blue car parked outside, then it must mean that there is. It all sounds very simple, but it's good to know how these things are fundamentally built up. So in this strategy, we prove that the negation of P is false by showing that it can be used to derive a contradiction. So the strategy is we say at the start of the proof, assume that the negation of the proposition holds, and then we do some work, and then we say, we've got a contradiction now, therefore P must be true. So for an example, this is the only example that I gave, which is not related to the work you're doing, but I included it because it's a very classic proof by contradiction. And if you haven't seen it before, then it's worth a look at. So apparently, one of Pythagoras' followers managed to prove this. And so the story goes, Pythagoras thought that every number was rational, and he didn't like the idea that it might not be rational, and he had the guy killed. I don't know if that's true, but it sounds like a fun story. Anyway, dangerous knowledge. So suppose for the sake of contradiction that the square root of 2 is a rational number. Well, what does that mean? It means that we can write it as a fraction of integers, okay? That's just the definition of what a rational number is. What can we do with this? Well, we can assume that the integers have no common factors apart from 1. Otherwise, we could just take the common factors out and reduce the fraction. And we can also suppose that q is non-zero, because otherwise this doesn't make sense. We're going to square both sides of the equation. Square root of 2 is equal to p over q. And we get that 2 equals p squared over q squared. Just multiplying both sides by q squared, 2q squared is equal to p squared. It's just this equation rearranged. And that means that p squared is even. Well, only even numbers square to make other even numbers, so p must be an even number. And we can therefore write it as p equals 2k for some integer k. Well, when we substitute this back into this equation here, we're going to get 2q squared is equal to 2k all squared, and therefore 2q squared is equal to 4k squared. And this is what you end up with. Q squared is equal to 2k squared, and because k is an integer, q squared must be even. And by the same logic, q is even again. Well, this gives us our contradiction, right? P and Q are both even numbers now. But at the start, we said, well, P and Q could be the reduced form of the fraction, and they share no common factors apart from 1. But if they're both even, they have a common factor of 2. So the assumption that the square root of 2 is rational must be false. And hence, square root of 2 is irrational. So like we said on the previous slide, we suppose for the sake of contradiction that the square root of 2 is rational. We do some work, we get a contradiction, and then therefore the thing that we supposed must be false. All right, so the next proof we're going to do, the next proof type we're going to talk about is proof by induction. And this is one that every maths student will have seen before. I don't know everyone's background, maths, computer science, something different, physics. So I've included it, and it's important to know the logic, but also the way that you kind of write this down matters. And I wanted to explain each step one by one so that you can have sort of a plan of how to attack these and a way of structuring your answers when you have a question to be answered like this. So there are 4 main parts to every induction proof. The induction proof should be used whenever you're asked that whether a proposition holds for every single natural number. So it's for a very specific type of proof. Only ones where there's you have to prove every natural number holds. So the basis step is to prove that the claim you're asked to prove holds for the special case for n equals 1. Then the assumption step, you assume that the claim holds for some arbitrary natural number, which we'll just call k. Now the induction step follows, and you show, given that your assumption holds, the claim must also hold for the case n equals k plus 1. And then you reach the conclusion. Because the claim holds for n equals k plus 1 whenever it holds for n equals k, well, we know that it holds for n equals 1, so the induction step applied to this proves that it's true for n equals 2. If it holds for n equals 2, then the induction step shows that it holds for n equals 3. And this kind of goes down forever. I like to think of it as though every case of the proposition for all the natural numbers is like a domino, and they're all standing in a of them. So the induction step is basically proving that if I knock a domino down, then the next domino falls down. And then the basis step is saying I pushed the first domino down. The conclusion tells you, every domino is going to fall. So we're going to explain this with an example, and this is to do with the set theory stuff that you did at the start of the course. So the theorem goes, every set S, which is a finite set and it has a natural number of elements n, has exactly 2 to the power of n many subsets. So this is the same as saying the power set of the set S is equal to 2 to the n in cardinality. So for the proof, the basis we start with, we're doing the case n equals 1. So if S has 1 element, then we can write S as the set containing the element that it has. Subsets of S are itself and the empty set, and therefore it just has 2 to the 1 many subsets, and that's the thing we were trying to prove. So we proved, I've knocked the first domino down. So we're going to assume that every finite set with k elements has 2 to the k many subsets for some natural number k. So this is saying, assume that some domino has been knocked down, and the induction step is to say the next domino must fall. So for the induction step, suppose that we have a set S and it has k plus 1 many elements. Well, we're going to write S as the union of some singleton set and R, and X is just, some element of S, and R does not contain S. It's just the set S, but without X in it. So R must have k many elements. because all I've done is taken a set with k plus 1 many elements, and I've partitioned it into 1 and the rest. So all the subsets of S, well, they either contain X or they don't. So they're either some subset of R, or they're some subset of R with X included in them. That seems kind of obvious, but what it implies is that using our assumption, well, the assumption was that if we have a set with k many elements, it has 2 to the k many subsets. So that's like saying the power set of R has cardinality 2 to the k. And because we have this claim here, subsets of R are the ones that are subsets of subsets of S are either the subsets of R or they are those subsets with X in them. We just see we've doubled the amount of subsets when we include this element X into S. So that's what tells us here that the power set of S has double the amount of elements as the power set of R, and that gives you 2 to the k plus 1, which is the thing we were trying to prove in the induction step. So because the claim holds for n equals k plus 1, whenever it holds for n equals k, we've shown that it holds for n equals 1, it must hold for every natural number n. Now, I'd be remiss if I didn't bring up for further reading that there is an extension of this, which it's so if you're into sort of further reading on set theory, then I recommend you look up transfinite induction. And the difference is that ordinals kind of continue past this set of natural numbers, and in fact, you could do induction on uncountable sets, but the difference is that you have to do a sort of second induction step for the limit ordinals. So don't worry about all of this if you've not encountered that before. This is just if you want to go above and beyond, look into transfinite induction. So the next type of proof we're talking about is proof by contrapositive. So this is another very important one to know, and it's one where people make a lot of mistakes, or people forget to try it and then they get stuck on a question because they didn't look at the contrapositive. So it's useful for when you're trying to prove something along the lines of P implies Q. The contrapositive of this statement is the negation of Q implies the negation of P. And in fact, every statement P implies Q is logically equivalent to its contrapositive. So what we can do, if we're asked to prove this, we can prove this instead. We can prove not Q implies not P. Why would we want to do that? Maybe P is some property which is a bit, some proposition which it's kind of like hard to discern the information from. It's kind of not clear how to derive Q from P. But when you look at the negation of Q, it's something that is very easy to get a grasp of. And sometimes, a light bulb pops up when you look at the contrapositive and you say, it's very easy to see why not P can be reached from not Q. So it's worth having a look at some statements, seeing what the contrapositive of them are, and then seeing, sometimes this is the best way to prove it is by contrapositive. So just a quick example for motivation. The claim, if I am water, then I'm wet, it implies the contrapositive claim. If I'm not wet, then I'm not water, and vice versa. But there is a common mistake. So a lot of people make this mistake, and it's where they get the contrapositive mixed up with the reverse implication. So not Q implies not P is the contrapositive of P implies Q. The reverse implication is Q implies P. And oftentimes, if Q and P are not logically equivalent, then you can't even say that this is true compared to this. And in the above example, if I am water, then I'm wet, the reverse implication is if I am wet, then I am water, which is not necessarily true. Well, it isn't true. I could be like orange juice or something like that. So yeah, this is logically equivalent to this, but not logically equivalent to this. And here's another topology example for the contrapositivity. And this is a more recent thing that you've been going over it, which is Hausdorff spaces. So it's the subspace topology on Hausdorff spaces and proving that it's also Hausdorff. So the statement is, let Xt be a topological space. let ATA be a topological subspace of X with the subspace topology. If XT is Hausdorff, then ATA is also Hausdorff. So to prove this by contrapositivity, we're going to show that if ATA is non-Hausdorff, then XT is non-Hausdorff as well. So assume that ATA is non-Hausdorff. Well, what does that mean? By definition, it means that we can find 2 points which cannot be separated by a pair of open sets. So precisely, if we have A1 and A2, which belong to our non-Hausdorff subspace A, anytime we have two sets A1 and A2, which belong to the topology of A, they're open sets, with A1 belonging to the first one, capital A1, and A2 belonging to big A2, we must have that they have non-empty intersection. We can't find two nice little open neighborhoods which don't intersect each other. So our goal, as I mentioned earlier, is to show that XT is not Hausdorff either. So we can write TA by its definition. So the set TA is just A intersect with all of the elements of the topology T, the topology on X. So a set is open on A if and only if it's the intersection of A and an open set on T. Well, because A is a subset of X, we know that A1 and A2 are in X. Okay, yeah, because they're in A and A is a subset of X, they must belong to X as well. Let X1 and X2 be elements of the topology of T, the topology T of X, sorry, with A1 belonging to X1 and A2 belonging to X2. So to prove that T is non-Hausdorff, we have to show that these necessarily have non-empty intersection. These are arbitrary sets X that we've picked from the topology, so it will show that it holds for all sets in the topology. Well, A intersect X1 and A intersect X2 belong to TA. This is just this definition we've written down here. This is this definition of the subspace topology. Well, we notice that A1 belongs to X1 intersect A because it's in both the sets X1 and the set A. And similarly, A2 belongs to X2 and A. And these both belong to the topology of A by the definition of the subspace topology. Well, because TA is a non-Hausdorff topology, the intersection of these two sets must be non-empty, right? This is our assumption we started with, which was saying that this is a non-Hausdorff topology. Well, that means these have a non-empty intersection, but X1 intersects X2 is a subset of superset of the intersection of these two sets. So X1 intersect X2 is non-empty as well. And that completes the proof. We've shown that whenever we take some arbitrary intersection of two sets in the topology, and one of them contains A1 and one of them contains A2, their intersection must be non-empty. Okay, so that's one which it's a little more involved because I understand you've only just got to the definitions of these concepts, so it might take a while for them to sink in. But this is one you should kind of like make sure you understand fully because it really helps me to understand the differences between Hausdorff and non-Hausdorff topologies. And lastly here, we've got some exercises. And so I've asked you here to complete your own proof 4 ways. So direct contrapositive, induction, and contradiction for the following claims. For some reason, this middle one's highlighted first. But so yeah, the first claim here is saying that if n is a natural number, then the sum of all the odd numbers up to 2n minus 1 is equal to n squared. Second one here, if n is a natural number, then if n is a multiple of 4, then n is a multiple of 2. Now, the reason I left this as an exercise, even though it's a completely, like, obviously trivial thing, is because sometimes it being too easy, trying to write proofs for things which are really, really easy helps you to kind of understand how to write the logic and to explain it. That the point of the exercise is that it's really easy, and the point of doing it 4 ways is to highlight the difference between these 4 methods of doing this. And lastly, if n is a integer, not necessarily a natural number, it doesn't have to be positive, then x squared, this should be n squared plus 2n plus 1 is positive. It's at least 0. Now, how do you do induction on this, given that it's an integer and not necessarily a natural number? Well, what you have to do is create some sort of bijection between the integers and the natural numbers, and then substitute that into here, and then perform the induction on the natural numbers. So lastly, today we're going to talk about counterexamples. So these are disproofs rather than proofs, but it's kind of one and the same, because disproofs of claims are just proofs of the negations of those claims. So counterexamples should be used whenever you're trying to disprove something of the form for all x, some proposition holds. And that's, as I said, the same as proving that the negation of for all x, p of x holds. So how do we negate this? Well, that's like saying there exists x for which the negation of p holds. And to do this, all we need to do is find an example of x where the negation of p of x holds. That's what existing means, right? And x in this case is a counterexample to the proposition for all x px. And you know this, if we found a counterexample, this proposition is incorrect. So here's an example for motivation. If I wanted to disprove the claim for all cars are blue, I can do this by showing that there exists a car which is not blue. That's obvious. Any non-blue car could be a counterexample to this. Now here's one common mistake. Sometimes people negate this statement wrong for all x px, and they write for all x negation of px. This would be like trying to disprove all cars are blue by showing that all cars are not blue. So that's not true, obviously. If you could prove this, then yes, it would imply that all cars are blue is wrong. But the problem is they're not logically equivalent statements. This is all cars are not blue is a strictly stronger statement than saying there exists a car which is not blue. Another common mistake that you see all the time is people trying to prove claims of the form for rather than to disprove them with a counterexample. And this is it's something which mathematicians maybe differ from a lot of sciences on, is by saying no matter how many examples you find me, I'm not going to believe it until you've proved that it holds in every single case. So for example, if I left an exercise which said, oh yeah, prove that if I've got a 2 by 2 matrix ABCD and it's invertible, then AD minus BC is equal to 0. What you have to do is prove that that's true. AD minus BC is non-equal to 0. The determinant is not 0. So to prove that, you have to show that it holds in all cases. But a lot of the time, people just write, okay, well, if ABCD is equal to 1, 2, 3, 4, then the determinant's non-zero. So all they did was find an invertible matrix and prove that the determinant was non-zero. They didn't show it happens in all the cases. And yeah, simply put, there exists x for which px holds is not going to prove that for all x px holds. When you write it like this, it does seem simple. So an example I'm just going to leave you with today is this non-theorem. So infinite sets always have the same cardinality. How do you disprove the claim that all infinite sets have the same cardinality? Well, all you have to do is prove that there exists 2 infinite sets which have different cardinalities, and those sets would be your counterexample. So, for example, the real numbers and the natural numbers are 2 infinite sets which have different cardinalities, which disproves the theorem. And I'll point you towards our video we made a few weeks ago now on Cantor's diagonal argument for how you prove this claim. That's definitely a proof that you want to know for the future. Okay, thanks everyone for listening. I will stop the recording and we can continue with any questions or discussion.